It's bigger than Oumuamua, it's older than our solar system, and it's moving so fast that nothing can stop it. Right now, a colossal object from deep space is hurtling through our solar system on a one-way trip past the sun. Its name is 3I Atlas, and it's only the third interstellar visitor we've ever found. But this one is different. It's larger, more mysterious, and possibly older than any comet or asteroid we've ever studied. And scientists believe it could hold secrets from the birth of distant stars billions of years ago. Could 3I Atlas be the most mysterious interstellar object ever discovered? In this video, we're going to explore everything we know so far about this incredible traveler, from its discovery to its strange journey through our solar system, its possible origin, and even the controversial theories about what it really is. Before 2017, no one had ever seen an object from another star system pass through ours. In 2017, we spotted the first one, Oumuamua. 2 years later, a second object, Borisov, confirmed that these visitors were real and perhaps not as rare as we once thought. And now, less than a decade later, we have a third, 3I Atlas. 3 interstellar objects in such a short time after centuries of seeing none at all. That is a staggering shift in our understanding of the cosmos. Each one tells us a little more about the galaxy. But 3I Atlas, it changes the game. On July 1st, 2025, astronomers at the Atlas Survey in Chile detected what appeared to be just another comet, a faint speck in the darkness, moving steadily across the sky. Atlas, short for Asteroid Terrestrial Impact Last Alert System, wasn't designed to find things like this. Its mission is to scan the sky for potential threats, asteroids on a collision course with Earth, using its network of telescopes in Hawaii and Chile. Every night, it captures thousands of images, flagging moving objects for further analysis. This object was one of them. At first glance, nothing seemed extraordinary. It was catalogued under a temporary designation, a 11PL3Z, another icy body, another orbit to compute. But something didn't add up. As the hours passed and data rolled in from other observatories, patterns began to emerge. Patterns that didn't fit any normal comet or asteroid bound to our sun. The orbit looked strange, too stretched, too open. By the next day, it was clear. This object wasn't looping around the sun like everything else in our solar system. It was on a hyperbolic trajectory, an open curve that doesn't close back on itself. That single detail changes everything. A hyperbolic orbit means one thing: it's not from here. It's coming in from interstellar space, and it will never return. Once the orbit was confirmed, the naming process began. The designation 3I Atlas is more than a label, it's a milestone. The I stands for interstellar, and the 3 marks its place in history. Before this, only 2 others carried that distinction. 1I Oumuamua in 2017 and 2I Borisov in 2019. Now, Atlas joins that elite group as the discoverer of the third. Its formal comet designation, C2025N1, Atlas, follows the standard format, C for comet, the year, and the discoverer's name. But 3I Atlas, that's the name that matters. It's a reminder of just how rare and precious these objects are. What makes 3I Atlas so extraordinary? In many ways, it is everything we've hoped to find in an interstellar visitor: massive, active, fast, and ancient. When the first brightness estimates came in after its discovery, astronomers immediately noticed something unusual. 3I Atlas was bright. Even accounting for its proximity and reflective coma, the numbers suggested an object much larger than either of its predecessors. As the models refined, the estimates stabilized around 11 kilometers across, possibly up to 15 kilometers if its reflectivity is on the lower end. To put that in perspective, Oumuamua was barely a few hundred meters long, comparable to a city block, while Borisov, the second interstellar visitor, was likely around 1 kilometer in diameter. This makes Atlas an order of magnitude bigger than Borisov and perhaps 50 times the size of Oumuamua. What does that mean in real-world terms? 11 kilometers is roughly the height of Mount Everest turned sideways, and then some. If it were placed over a city like New York, its icy surface would stretch from Manhattan to the Bronx, dwarfing the skyline. This is not a fragment or a shard. It's a fully developed body, comparable in size to some of the largest comets in our own solar system. However, these measurements come with a significant caveat. Most of what we see right now is not the solid nucleus itself, but the bright coma surrounding it. When a comet approaches the sun, heat causes its ices to sublimate, creating a halo of gas and dust that can be thousands of times larger than the nucleus. That makes it hard to pin down its true size. Astronomers rely on complex models of reflectivity, activity rates, and gas production to separate the coma's contribution from the solid body inside. Current estimates suggest the nucleus itself falls in the 11 to 15 kilometer range, but even if that's off by 20%, it remains the largest interstellar object we've ever observed. This size is more than a statistic. A larger nucleus means more material to study through its emissions, which in turn gives us a more detailed chemical fingerprint of its origin. And because bigger objects tend to survive longer journeys without breaking apart, 3I Atlas may have preserved its primordial structure from the time it formed, billions of years ago. Then there is its speed. At interstellar speeds, numbers become difficult to grasp, but let's break them down. Relative to the Sun, 3I Atlas is traveling at about 58 kilometers per second right now, and it will accelerate slightly as it swings around the Sun, peaking near 68 kilometers per second. That's roughly 150,000 miles per hour, fast enough to cover the distance from Earth to the Moon in under 2 hours. For comparison, Earth itself orbits the Sun at about 30 kilometers per second. Voyager 1, humanity's fastest spacecraft, crawls along at just 17 kilometers per second. 3I Atlas is moving nearly 4 times that speed. Its trajectory is equally striking. Unlike most objects in the solar system, which orbit in the same general plane as the planets, 3I Atlas approaches on a retrograde path, cutting against the direction of planetary motion. Its inclination is only about 5 degrees off the ecliptic, so it's not plunging in at a wild angle like Borisov did, but its retrograde orbit ensures an extremely high relative velocity when passing near planets. It will make its closest approach to the Sun on October 29, 2025, at a distance of about 1.36 astronomical units, just a little farther than Earth's orbit. On its way in, it will pass Mars at roughly 0.19 astronomical units on October 3rd. Earth's closest encounter comes later, on December 19th, when the object will be about 1.8 astronomical units away, safe but well within range for powerful telescopes. From there, it will arc past the Sun and sail back into the void, never to return. Perhaps the most profound question about 3I Atlas is not where it is going, but where it came from. Based on its trajectory, scientists calculate that it entered our solar system from the direction of Sagittarius, a region of the sky near the galactic center. That doesn't mean it originated there. These objects can wander for billions of years, deflected by encounters with stars, clouds, and gravitational tides. Its speed and approach vector suggest it is not part of the galactic thin disk, where most stars like our Sun reside, but likely the thick disk, a population of older stars orbiting in a puffier halo around the Milky Way's plane. If that's true, this object could have formed when the galaxy was young, perhaps 3 to 11 billion years ago. Think about that for a moment. This fragment of ice and dust might predate our solar system by billions of years. When it formed, Earth didn't exist, the Sun didn't exist. Life, as far as we know, didn't exist anywhere nearby. Yet this object has survived unaltered, ejected from its birthplace, perhaps during the early chaos of planet formation around another star, and left to drift through interstellar space for an almost unimaginable span of time. Unlike Oumuamua, which baffled astronomers by showing no obvious signs of outgassing, 3I Atlas behaves like a classic comet, though on an interstellar scale. Even at its current distance, it is already active, shedding dust and gas into a diffuse coma tens of thousands of kilometers wide. That activity will intensify as it approaches perihelion in late October, when solar heating ramps up. By then, it could develop a spectacular tail stretching millions of kilometers through space, visible even to modest telescopes under dark skies. What will that tail look like? Early models suggest a combination of dust and ion tails, shaped by solar radiation pressure and the solar wind. The dust tail will curve gently along its orbital path, while the ion tail will stream straight back, glowing faintly blue from ionized gases like carbon monoxide and cyanogen. The chemistry of that tail will be a goldmine for spectroscopic analysis, revealing not only the ices that dominate its surface, but also trace compounds, organics, carbon chains, maybe even prebiotic molecules. This is not just an aesthetic detail. The nature of its activity tells us about its structure and composition. The rate of gas production can constrain its size, porosity, and thermal properties. The relative abundances of CO, CO2, and H2O can hint at the temperature and environment of its formation. In short, the tail is a diagnostic tool, a natural probe that lets us sample material from another planetary system without leaving home. All of this, its immense size, blistering speed, ancient origin, and vigorous activity, makes 3I Atlas unique among interstellar visitors. Oumuamua was strange but fleeting, leaving us with more questions than answers. Borisov gave us familiarity, but limited detail. Atlas offers both scale and substance. It is big enough to study thoroughly, active enough to reveal its chemistry, and close enough for our best instruments to capture every photon they can. For planetary scientists, this is as close to a time machine as we're likely to get, a messenger from a deep past, bearing secrets from a world that died before our sun was born. When 3I Atlas was confirmed as an interstellar object, it set off a chain reaction across the global astronomical community. Observatories scrambled to secure observing time, and for good reason. This is a once-in-a-lifetime opportunity to study material from a star system other than our own, without leaving Earth. To maximize what we can learn, the most powerful instruments ever built are now aimed at this icy traveler. Hubble Space Telescope is already on the case. Its ultraviolet and visible light instruments are perfect for probing the composition of cometary comas. By analyzing sunlight reflected from the dust and gas around the nucleus, Hubble can identify signatures of water, carbon monoxide, carbon dioxide, and other molecules. These observations are critical because they reveal what this comet is made of, and that chemistry is our best clue to the environment where it formed. Then there's the James Webb Space Telescope, the most advanced infrared observatory humanity has ever launched. Webb's instruments are uniquely suited to detect ices and organics because many of these molecules emit or absorb strongly in the infrared. Webb can see past the glare of the coma and look for specific spectral fingerprints, bands that tell us not just that there's water or CO2, but in what ratios. These ratios matter. They encode information about the temperature and pressure conditions during the comet's birth. A high abundance of carbon monoxide, for instance, suggests formation in a very cold region, far from a star. If Webb detects complex organics, chains of carbon and hydrogen, perhaps even nitrogen-bearing molecules, that would push the implications even further. On the ground, telescopes like the Gemini Observatory, the Very Large Telescope, and upcoming facilities, such as the Vera C. Rubin Observatory, are mounting intensive campaigns. They use both spectroscopy and imaging to track how the comet evolves as it approaches the sun. By comparing data from multiple wavelengths, optical, near-infrared, submillimeter, we can build a full profile of its outgassing rates, dust-to-gas ratios, and rotational characteristics. Instruments like ALMA, the Atacama Large Millimeter Submillimeter Array, can detect molecules that emit in the radio and submillimeter range, providing another window into its chemistry. How do these measurements actually work? It's all about light. Every molecule interacts with light in a unique way, absorbing and emitting at specific wavelengths. Water, for example, has strong bands in the infrared, while carbon monoxide emits in the submillimeter. By dispersing the light from 3I Atlas into a spectrum and comparing it to known laboratory data, astronomers can identify these molecules with exquisite precision. And because these telescopes can separate light by wavelength so finely, they can even measure isotope ratios, like the ratio of deuterium to hydrogen in water. That ratio is a fingerprint of the environment where the water formed. Compare it to Earth's oceans, and you might begin to answer one of the oldest questions in science. Where did our water come from? Every observation of 3I Atlas is a data point in a much bigger puzzle. What does the chemistry of other planetary systems look like? If this comet has similar compositions to our own, that might suggest commonality, that planet formation follows similar rules across the galaxy. If it's radically different, that tells us diversity is the norm. Either outcome is profound. Could some of Earth's own ingredients, water, organics, have originally come from beyond the solar system? It sounds far-fetched, but consider this. The early sun formed in a cluster with thousands of other stars. Interstellar objects like 3I Atlas are not rare on galactic scales. They are constantly being ejected during the chaotic early stages of planetary formation. Our system likely lost countless comets to interstellar space, and it may have captured some from other systems in return. If that happened, then the seeds of life on Earth may include contributions from distant stars. Studying this object could tell us if the chemical building blocks of life, carbon chains, nitriles, perhaps amino acid precursors, are common in other systems. If they are, then life might not just be possible elsewhere, it might be inevitable. Even beyond biology, this is a chance to test our models of planetary system formation. For decades, those models have relied on the chemistry of our own comets, but that's like trying to understand all of Earth's ecosystems by studying a single forest. 3I Atlas offers a sample from an entirely different environment, one that formed under conditions we can only guess at until now. As monumental as these observations will be, they also highlight a limitation. We can only watch from afar. Imagine if we could send a spacecraft to intercept 3I Atlas, collect samples, and analyze them up close. The science return would be extraordinary, arguably one of the greatest in history. The problem is time. 3I Atlas was discovered in mid-2025, and it will already be outbound by the end of the year. There's no way to build, launch, and rendezvous with it in time. But that hasn't stopped scientists from dreaming and planning. ESA's Comet Interceptor, scheduled for launch later this decade, is designed with this exact scenario in mind. It will park in a stable orbit near the L2 point, waiting for the alert of a new comet, possibly even an interstellar one. When that happens, it can swing into action, using pre-built instruments to fly by the target and capture close-up images and data. NASA is exploring similar concepts, rapid response missions that can launch on short notice when an object like this appears. The key is readiness. If we had just a few years' warning, we could send a probe to meet one of these interstellar visitors. Someday that might even mean a sample return. These ideas aren't science fiction, they're the logical next step in planetary science. Each interstellar object we find reminds us that the galaxy is interconnected. Our solar system is not isolated, it exchanges material with the broader Milky Way. The ultimate goal is to hold that material in our hands, to study it in laboratories, and to read the story it carries, a story that began around a distant star billions of years ago. This is why astronomers are obsessed with 3I Atlas. Where did we come from? How common are the building blocks of life? What does a planetary system look like beyond the faint glow of our sun? For now, those answers are locked in a nucleus of ice and rock, racing past us at 150,000 miles per hour. And every telescope on Earth and beyond is trying to catch them before they're gone forever. When an interstellar object makes headlines, speculation about alien technology is never far behind. It happened with Oumuamua in 2017, and now it's happening again with 3I Atlas. The most prominent voice in this debate is Harvard astrophysicist Avi Loeb, who recently published a paper suggesting the possibility, however remote, that 3I Atlas could be an artificial object, even a probe sent by an extraterrestrial civilization. His argument draws on the same reasoning he applied to Oumuamua. When something behaves in an unexpected way, we should at least consider unconventional explanations. In his recent preprint, Loeb speculated that because 3I Atlas is unusually large for an interstellar visitor and exhibits a retrograde trajectory, It might be part of an intentional design, or even a remnant of alien technology. He even went so far as to reference the dark forest hypothesis from science fiction, which suggests that advanced civilizations might camouflage or weaponize probes for survival. It's an attention-grabbing angle, and it makes for sensational headlines. But does the evidence support it? Most experts say no. Unlike Oumuamua, which lacked a visible coma and exhibited unexplained acceleration, 3I Atlas behaves exactly like what you'd expect from a natural comet. It has an active coma and tail. Its orbit follows a clear hyperbolic trajectory, consistent with gravitational interactions, and there's no sign of propulsion or controlled maneuvering. In other words, it looks like a comet and acts like a comet. That doesn't make it boring. Its origin, composition, and age are fascinating, but it does mean we don't need to invoke alien engineering to explain its properties. This raises an important point about scientific reasoning. Extraordinary claims require extraordinary evidence. With Oumuamua, the lack of a coma and the anomalous acceleration opened a legitimate mystery, though most explanations eventually focused on natural processes like outgassing of molecular hydrogen or nitrogen ice. With 3I Atlas, we don't even have that level of anomaly. So while the idea of an alien probe makes for exciting headlines, it's not a hypothesis supported by the data we have so far. That said, there is a lesson here from the Oumuamua debate. Stay curious, but don't jump to conclusions. Science thrives on skepticism, not cynicism, but a willingness to question and test every idea, no matter how wild, while grounding those questions in evidence. If we ever do find something artificial, it won't be because we leapt at the first opportunity to declare it so. It will be because we gathered data that left no other explanation. So where does that leave us? For now, 3I Atlas appears to be a natural object, a relic of another star system, billions of years old. But its journey through our solar system still gives us a chance to learn about the galaxy in ways that were impossible just a decade ago.